Okay, so fantastic. Thanks everybody for joining. This is the Sensorium competition and our 2 to 3 hour workshop. And yeah, thanks for being here, everybody. It's late in Germany, so let's try to keep this within 2.5 hours. So we have quite a few people from the Sensorium team joining here. You can see us or recognize us based on the hoodies. So the two first prize winners will also get some hoodies in the mail soon. Yeah, maybe we can make a quick show of hands. Who of you have did participate in the competition and made an entry? You can make a show of hands in the Zoom. Okay, that is a few. Alrighty. So we also try to do this a bit interactive. So let me share the screen for the presentation. So everybody, yes, welcome to our workshop today. We'll first have a, let's say, 25-30-minute talk about what this is about, introduction about this competition. We have then talks from the winners who are also here about the modeling approach. Then we have 2 invited talks. Then Dean will talk about how good your model will be if you had an infinite amount of noiseless data. And we have Grace Lindsay talking about predicting mouse neural activity with models trained through supervised, unsupervised, and reinforcement learning. And then at the very end, we'll discuss about the competition and discuss about some lessons learned, which Paul will talk about. And so, yes, we'll still try to make this interactive. So whenever you have questions or comments, raise your hand or just speak up. Alrighty. So I'm not sure how familiar everybody is with the competition. So I first introduce the whole thing, talk about what our intuition is, and then what the results are. Alrighty. So I first talk about what is our Sensorium competition, what we hope to learn from it. I will talk about the competition tracks and the data, and then finally also a primer on the results. Alrighty, so what is the Sensorium competition? Our goal is to predict the activity of neurons in the primary visual cortex of mice in response to natural images. So what this is about is we have natural images and we show these to real behaving mice and we record the neural activity in response to those images. And then we also train models or come up with models that predict this activity. Then we compare some kind of metric, some kind of score that tells us how accurately can we model this recorded activity based on those images. And then we just simply score on some leaderboard the best model and give prizes for it. And we have the winners here talking about their modeling approaches later on. So a quick overview of the timeline of this competition. So this year in May, we got the acceptance of this competition at NeurIPS. On May 20th, we announced that it's going to happen. On June, we started, June 20th. And until October 15th, the model submission was open. So it was about 4 months' time to come up with the best predictive model. So what do we hope to learn from this kind of competition? And this is especially timely because machine learning and neuroscience are at the moment co-developing quite nicely. So there is currently quite a large body of knowledge about the early visual system. And so let's say retinal ganglion cells, receptor fields, tuning of simple complex cells, all of this, there's been quite a lot of progress. And it's fair to say that CNNs are inspired by the knowledge of the logical visual system. But fair enough, it's mostly just inspired by some, let's say, knowledge that has been acquired quite distant in the past. But what is nice is that the early visual system of the CNNs display quite similar properties as the early layers in visual cortex. So that's quite nice. And then in turn, using those CNNs to build models of neural activity or build models of visual cortex has also been shown to be a kind of productive research avenue. We can make use of this hierarchical processing or make use of this fundamental approach of using CNNs to model the visual hierarchy. But then there is a problem, and it's basically a productive problem, that even quite early on in the visual hierarchy, it's not clear what the full properties of this area are. So even already in V1, we cannot confidently say that we've understood it fully. So modeling the activity of a brain area is a good way to figure out how much have we understood about this area and what maybe is still missing. So for a benchmark like this, what do we really want to learn? Or put it differently, what do we really learn by running a benchmark and predicting some kind of high number? So a benchmark that would just optimize some one-dimensional metric is scientifically not interesting on itself. And we've gotten this criticism before, and it's a fair point. By just having a great prediction itself is not interesting. But when it starts to be interesting is when we make those models interpretable. We actually want to learn something. And there have been a number of successful approaches that are in silico and closed loop experiments who make these black box models work for very interesting and deep biological insights. So there have been closed loop experiments on macaque V4. This is by Kaiwen and Di Carlo. A similar approach for mouse V1, and the most exciting inputs showing that what mouse V1 cares about is more complex than Gabor's. And then there's also closed loop experiments about color processing and the behavioral state in mouse V1 that we've shown recently. So all these approaches kind of highlight how a good predictive model can be used to actually gain insight. All right, so our goal with this competition would be, first of all, we provide a large-scale data set of neural activity in V1, so a kind of a benchmark data set. And we use this to measure progress in how well V1 is understood. Again, with a benchmark of, let's say, best predictive performance. We also want to basically use this opportunity to compare evaluation matrix, because there's quite a few around and they differ in interesting ways. And that's what Dean is going to talk about later in this workshop. And finally, our long-term goal is to use essentially interpretability methods to then make those black box models work for us scientifically and to gain insights into visual processing. Alrighty, and I want to mention some related work. So our competition is not the first competition or not the first benchmark for neural data. There also has been the RAIN score. I guess many people are familiar with this one. That is also like benchmarking neural activity, but the goal is slightly different. So the goal is to find models that are both well predictive of ImageNet categories, but also neural data along the ventral stream. But it's also different because the neural data is not available and it's not the primary goal. And in turn for us, for Sensorium, the neural data itself is the primary goal. And then there's also the Argonauts challenge. Maybe also some of you have heard of this. This is human fMRI data. And so this is a data set of human fMRI activity, or just voxel activity of the visual stream in response to natural videos. And then the challenge is to predict voxel activities. So if you haven't seen this yet, it's also worth checking it out. Okay, but now back to our Sensorium competition. So this is the data that we have. Data that we provide is it's images, and then the activity in mouse visual cortex. And then again, the goal is to fit some kind of model and predict this activity. And how it looks exactly like, we have a set of training images and then repeated or testing images. And how the data set is composed of is the mouse gets shown individual images with some grays green excuse me in between. And then for each neuron, we have a scalar response to this image. We have many images and many neurons. And then we have two different kinds of test sets. And in these test sets, the responses to those images are withheld. And finally, the score is computed, or the competition score is computed on these two different test sets. So that's the Sensorium track on the left, and with the Sensorium Plus track on the right. And there we also provide the behavioral data. So we have behavioral data for locomotion speed. So the mouse is sitting on the treadmill, and as it's running, we can record if it's moving and how fast it is moving. And we also record the pupil size and the change of pupil size and where the eye is looking at the moment. So let's say mice can't really fixate, so we let the mice move the eyes freely, but we track where the eyes are looking. Alrighty. And then we also provide not just these two data sets. So these two data sets are from one mice each, but we also provide 5 other data sets that are very similar in kind, but from different mice that are just designed to just have more data. So what we have is 2 competition tracks. We have Sensorium and Sensorium Plus, which has the behavior. And in total, for these 2 competition tracks and these 5 extra mice, we have 25,000 single neurons from primary visual cortex on mice V1. And for these 25,000 neurons, we have the activity in response to more than 5,000 images. And as behavior, we have eye movements, pupil size, and locomotion activity. And how we score this competition is with the held out test sets. And we have a live leaderboard. I'm sure many of you have seen this on the website. And for this, the live test set is being used, which are 100 images. And the predictive performance on this live test set will be displayed directly on the leaderboard. And we have our final hidden leaderboard, where the other test set is being used. And this is basically to prevent overfitting on the test set at the very end. All right, and how do we evaluate the entries? It does work with uploading the predicted responses on the competition website. So the dataset can be used freely, of course, but then to make an entry to the competition, the predictions of the held out test sets have to be uploaded. And then, for example, it looks like this. So this is one example unit. And then for this unit, we have the neural response on X and some predicted performance on Y. And then we can just calculate the correlation between predictions and responses. And with a particular neuron, it's the correlation of, let's say, 0.5. And we can do this for a couple of neurons. And the total competition score is the average across all these neurons that we have. And it's about 8,000 per competition track. And then, so all neurons get averaged into this average score. And this will determine, this did determine the winner of our competition. So it's the average score across all neurons. Okay, let's get to some results. So the results are displayed on our competition website at sensorium2022.net, and we have our leaderboard there, and they have the final test set is public. What we we were very happy to receive more than submissions from 26 different teams. And those teams submitted 149 models. And both competition tracks, we found new state-of-the-art models. So how did it look like? So this is a general overview. We have the Sensorium score, the final test set on the top, and the Sensorium Plus score at the bottom. And for Sensorium, I'm showing you the top line is a state-of-the-art line, or state-of-the-art performance. But of course, it's a bit difficult to say like what is state-of-the-art, since there's so many models around. Essentially, with this data set, we want to find what is state-of-the-art. And the baseline was a simple LN linear nonlinear model. So now this is how the scores over time developed. So again, gray line is a simple LN model. The black line was the model that we made public on our competition repository. And you see that there were quite a number of models that read our best approach. And how is look for Sensorium Plus? Also there were some models that were outperforming us quite nicely. Okay, and we also have some results more in detail. So of course, with all these predictions and all these responses that we have, we can look at the results in a more fine-grained way. So we here as an example, I'm showing you here for all the neurons in Sensorium, so it's about 8,000 of them. I'm showing you the performance as correlation to average. I'm showing the performance on our baseline model on X, and on Y is the performance for the winner for rank 1. So there we can see they correlate quite nicely. And the question, of course, then would be, what is the difference between rank 1 and our model? Do they predict certain neurons better than others? Did they do a better job on the low-performing ones, for example? So there's a lot of insights to be gained from this. And I want to show you this. I hope it does play. So here I'm going from, on the y-axis, we go from rank 15 to rank 1 to see how the models improved for all the neurons. So this is just a descriptive result for now, and we have to, and we will dig deeper. What is the actual difference between those models, and not just on the entire set of neurons? All right, and so where do we go from here? Dean, please go ahead.
I noticed that it seems like there's a belly that you see the most deviation in the center, and I can't tell if that's a statistical result of just most of the neurons having middling sort of R values, but it does seem like everyone gets the top neurons and everyone sort of gets the bottom neurons, but then it's these intermediate neurons where everything disagrees. Do you see any indication that that's true?
Yes, that's a good point. And I think the way that I'm plotting this here might not be the best one, because what we have here is those are 8,000 data points. So I think just by the nature of it, I think there's just many more data points actually in the center. And so of course the variance will also be then larger in the center. But I agree that especially in this middle belly, you see that the improvement happens. And I think this is true, but we didn't analyze it properly yet. Yeah, thanks. All right. So where do you go from here? So we have this benchmark, and the NeurIPS competition itself has been, let's say, one period where we want to find the best model, but the benchmark is still open for submissions. So we want this to be open in the next years, to have a continuous search for the best model for this particular set of benchmark data. And so the best predictive model of, let's say, mouse V1 with this kind of extensive data set. And from here, of course, we would like to run more competitions with new data in the future. Okay, are there other questions up to this point? Okay, I don't see a raised hand here, so let me then go to the schedule. So the workshop today, then next up will be talks by the winners. Also, the top 3 models of each track are here to present the modeling approach, which will take about half an hour. Then we have an invited talk by Dean. Right after, an invited talk by Grace Lindsay. And at the very end, we have a concluding discussion and some lessons learned from this particular benchmark and possibly future benchmarks. If there's no further questions, then I would suggest we will go straight to the winner talks, and we will start with the Sensorium track and Sensorium rank 3. So Simone, feel free to take it away.
Okay, sure. Thank you very much. Let me try to share the screen. Okay. Can you see it?
Yep, looks great.
Okay. So let me try to enlarge it as well. Okay. Thank you very much for organizing such a very nice competition and for setting up this framework. And today I'm going to talk about our approach. And first, I'm Simone Azeglio, and I'm a PhD student at the Vision Institute in Paris, which is part of Sorbonne. And I'm also spending part of my PhD at École Normale Supérieure, always in Paris. Our approach to this competition consisted in building on top of the baseline CNN model developed by the organizer, which is made by a nonlinear core, CNN layers, and a readout layer, which is informed by the biological retinotopy. We decided to focus on front-end modules, which are inserted between the input and the core, and in particular, we opted for 2 architectures. The first one, scattering networks, which enforces geometric constraints introduced by Bruna and Malat, and the second one, the V1 block, developed by Dappel and collaborators, which enforces biologically grounded constraints. The first ingredient, so the scattering networks show different interesting properties. The first one is that representation are not only translation equivariant, but also stable to small deformations. And the second one is that we can get a deeper model with respect to the employed baseline model without additional parameters to learn, because all the parameters are fixed in scattering networks. And to get a scattering network, for sure, we need different components, and one is 2-dimensional wavelets, which are obtained by scaling and rotating a single bandpass filter psi. For example, the so-called Morlet complex Morlet wavelet, where J represents a scale index and R represents rotation, where G is a discrete and finite group of in R2, for example. And to get a scattering network, we also need to convolve our signal with a wavelet and to apply a nonlinearity. So in this way, we can get translation invariant representation. And here I'm making it short, but the modulus is quite nice nonlinearity for our purposes. We also need at this point the notion of hierarchical representation, where we further iterate the wavelet transform and the modulus operator. If we define U as the modulus operator with lambda, which is basically the set of parameters that we need, we can iterate this on a defined path P by composing multiple times this U operator. And after that, we can get a scattering transform by convolving this operator U on a path P with a localized spatial window, spatial function, which enable us to keep the spatial variability at a larger scale than a fixed big J. So here we have the scattering transform applied iteratively. And as you can see, we can start with F, which is in general a function of the input. And we can go forward in this tree, and we can get a different application of U, and thus a path P, which is lambda 1, lambda 2 in this example. And doing it iteratively means basically to go to different order of this operator. And in practice, this means basically tessellating the spatial frequencies in a finer and finer way. A very fast example is these two textures, which they basically have the same Fourier spectrum, but at the first order of the scattering coefficient, we get a very similar representations. But by going deeper, for example, you can see how very different these two representations are. Together with this, we also, as I said before, add another ingredient, which is the V1 block, and which is more biologically grounded. It's based on a linear nonlinear Poisson model with Gabor filter banks that have fixed weights, so multiple orientations, sizes, shapes, and spatial frequencies, simple and complex cell nonlinearities, and neuronal stochasticity, which is basically obtained by adding an independent Gaussian noise to each unit of the block. This is the Carlos Lab architecture. We basically try to keep it small by reducing the number of simple and complex cells and by adapting it to rectangular images. This architecture were first obtained as an adversarially robust model to ImageNet classification, and they realized that by having an adversarially robust model, this also positively correlate with the explained variance in macaque V1. So we try to embed it in our modeling approach. And the last ingredient is, unfortunately for science, ensembling, where we started with the first model. As I said, we used one front end, the baseline architecture. We got some responses. We do the same for the V1 block. And we also do the same by changing the core with a squeeze and excitation CNN. Again, by applying the two different front ends, we do an ensemble average at the end, and we obtain an average signal. The live test results show an improvement where in the correlation to average, which is the evaluation metric for all the models. And of course, by ensembling, we got an even larger score, which allowed us to be third in the final leaderboard. And very few comments on one try and fail technique, which is basically trying to adapt the image to the eye optics, which is indeed a spherical projection. And by adopting the approximation where the geometry of the thin lens is not respected, we basically get transformed images. I tried to do that, but unfortunately it didn't work as expected so far. Maybe some more hyperparameter tuning are needed, but I'm curious to hear more about the comments about this approach. And my previous experiences as I've been working on the brain score competitions, and I've also been fitting data in the auditory pathway of the mouse by working with Brice Batelier at Institut Pasteur. And finally, I would like to thank my 3 supervisors and my whole team at Institut de la Vision. So thank you very much.
Thank you. Fantastic.
For being 1 minute late.
No problem at all.
Thank you very much
nice.
again.
Are there any questions about this particular approach? Yeah. So we're going to hear quite a bit more about ensembling from the other winners, but this is it's the winning technique. Okay, we have congrats to your third place on the Sensorium track. Now let's get to the second place. The speakers cannot be here today, unfortunately, but they've sent in the video. Let me share the video and then see what they have done. Okay, I hope you can all see this.
Hello, everyone. We are glad to share our approachment for the Sensorium competition. We are Team ZYE Go, and we are from Tencent AI Lab. Let's begin with a short introduction of challenge task. Given a set of grayscale images, we were asked to design a neural network to predict neural responses in the mouse visual cortex. The predicted responses should be correlated with the real responses as much as possible. The only thing we know in this task is the input image, so it's a very challenging task. Our model builds on baseline methods. We do not modify the original architecture, but 5 improvements in red font. They are adding gradient map as input, adding correlation loss, pre-training on multi-mouse, self-knowledge distillation, and greedy ensemble strategy. Next, we will introduce those modifications one by one. As far as we know, the neurons located in the V1 area of the visual cortex are responsible for processing primary semantic information, including the orientation information of the image. We found that the feature map of the first layer of the baseline model looks like an edge map, which means that our network is trying to analyze the gradient of the input image. Therefore, we utilize Sobel operator to extract the gradient of the image along the X and Y directions as part of the input. This modification freed up the network to focus on predicting neural responses. Loss function is a key module in neural network design. In this competition, we evaluate a model by calculating the correlation metric. This evaluation metric focuses on the correlation of all responses, rather than just the specific value of a single response. Whereas the original Poisson loss only builds supervision on a single response while ignoring the connections between different neurons. Therefore, we add a correlation loss to make the predictions of the neural network more holistic. Lambda is a constant to balance 2 loss. To utilize data from different mice, a general idea is to pre-train the network. However, the recorded neurons are different. So we pre-train the network using a share core and separate readout head. Afterwards, we fine-tune the mouse model. Pre-training enables our method to make great progress. To tap the potential of the model, we design a 2-stage self-distillation learning strategy. In the first stage, a teacher network is obtained based on the training set. In the second stage, we distilled the teacher network into the student network to obtain more robust performance. The flowchart and performance improvement are shown in the figure. Ensemble is a common trick in deep learning. We trained more than 100 models with different initial seeds and different numbers of neural network layers, but most of them were redundant. We design a greedy ensemble strategy to weed them out. The algorithm is shown on the right. The key idea is to ensure that each integrated model can improve the score on the validation set. Here is our fractional growth graph. Improvements are made with each revision. In addition, we also try to pre-train the core based on clip to shorten the distance between the image domain and the response domain. This allows our network to converge faster, but does not increase the performance. We think this is a point worth more exploring. In summary, data is important. Good design of network and training strategy is necessary. Some tricks like ensembling always work in deep learning competition. That's all. Thanks for your listening.
Okay, great. Yes, that was the video that rank 2 of Sensorium was sending in. And yeah, then let's go to rank 1 of Sensorium, which is Kaiwen. Please take it away.
Yeah, I'm here. So just let me share my screen.
quick question: are you going to talk about both model approaches?
Yeah,
or-
I'll
Yes?
talk
Okay.
about both because I think
Okay, yeah.
I just did some minor modification in Sensorium Plus, so I just
Great.
decided to combine them together. So hi everyone, my name is Kaiwen. I'm the second year PhD candidate in the Department of Computational Medicine and Bioinformatics from the University of Michigan. And today I would like to present our solution for the 2020 Sensorium competition, both the Sensorium and Sensorium Plus track. So it is my first time to train a model on the neural data. So we've just found it very interesting competition. So the major our major modification on the data are mainly on the input part, because we found it's very hard to modify the neural network structure because the baseline has already very high state-of-the-art model. So our major motivation just come from the Sensorium Plus track, that when we add the populous behavior, it improved the baseline performance. So we just wondering if that some areas in the images should be more attractive to the mouse. And we hypothesize that the object in the image may contain more information than the other areas. So we decide to first to detect the object position or the areas that contains more information, and then add the object position or the area position to the input of the model. So we just pre-train an object detection model using the YOLO version 5 large backbone, and using the data from the ImageNet's object detection competition in 2017. The reason why we use that because that's the official provided weight, the YOLO V5 large weight is retrained from COCO, and some important classes, just like the snake, is not in that dataset. So we just use the other dataset for pre-training. And in the final labeling, we also use the YOLO COCO, because actually in the ImageNet, they do not have the class for person. That's the problem. So we just use the YOLO ImageNet to detect the other objects, and YOLO COCO to detect the person. And finally, for a given input image, we will detect all the possible objects. We do not require the model to be accurately detect the objects classes or the object. We just want to find if the model think this area should have more information or not. And then we just merge all of the bounding boxes and pad them to a whole rectangle. And we will use the information as in the YOLO format, the X, Y, and Y and heights of the bounding box as the input of our final model. And there's other minor changes in our model is that we first we will normalize the data and normalize the image, centering the image, just like the use of the pixel, just subtract the average of all the pixels and add them as an additional channel, and use the convolutional layer to scale, to replace the scaling operation in the baseline model. And then we just increase the channel numbers in the network for encoding the images. And finally, we ensemble the models with different train validation splits. So this is the figure to illustrate our changes. So for the input, there's actually a 6-channel images, 6-channel input. The first channel is the images that is normalized using the baseline code that is normalized by the meta statistics, the mean and standard deviation. And then the second channel is the centering operation on the first channel. And the other 4 is the bounding box position. And the other 4 channels is the bounding box positions. And for the scaling part, we just use a convolution layer by setting its filter size and stride size equal to 4 to scaling the images to the 1/4 from its original sizes. And in the encoding part, we increased the filter numbers from 64 to 128 and 2056. And then to the ensembling part, we trained 10 models with different train and validation split. And then to ensemble the models, we just calculate the average predictions of all of these 10 models. And then for the Sensorium plus Sensorium plus task, the major motivation is just come from how we pre-train, use the other data set to help our training on the data set. The problem is that we found that the implementation of pre-training in the Sensorium track cannot use in the Sensorium plus track. So we just find a solution that is another type of ensemble. Like we choose a specific data set, and we will train a model with another data set as the helper. And we just repeat through all of the other data sets, and then average these predictions from these models as the final prediction as our for our target data set. This is just a simple figures for our operations. So there's some failed experiments. The first one is that we just try to make some augmentations, but we finally found that any operations that involve too much modification on the image information will significantly ruin the performance of a model. Like the like the random flip, it just changed the object position, so the performance just quite not well. And we also try the other operations that's how to utilize the object position. Like we just crop the image, crop the part where the object lays, and let the model just have the input from that part. And we also find that if the image loses the information of the surrounding part, the performance will also drop. And we also try to use the GradCam, that is a visualization, this interpretation skills to method to interpret the neural model, and use the GradCam results and add the GradCam result to our model, and found that none of them will work in my model. And in the Sensorium part, we just surprisingly found that when I also add the object detect opposition to our model, and the model performance will drop. We guess that it's because our object position is just an approximation of the true popular behavior. So if we add the wrong information to the model will just confused. And thank you very much for organizing such a fantastic competition. I would like to also thank my mentor, Dr. Yuan Guan, who just gave me a lot of suggestions on this competition. And that's all.
Yeah, thank you. That was great.
I would actually have a question. That's okay. Did you ever try to shuffle the bounding boxes across samples to basically to see how? I mean, they add something in addition, and they seem to help. But if you destroy that, and if you give the model the wrong bounding box for an image, does the performance also decrease?
Oh, that's a good question, but I haven't tried that. Yeah, okay. That's a good point for to improve our stability of our model, actually.
Yeah. Thanks.
Yeah, I have a quick question. So did you try using like center crop? Because you can see from the images that most of the objects there, in the center of the image. So you can like try to use this prior instead of
yeah, I tried center
making
crop. Yeah. Yeah, so not the center crop. I think it's not your center crop, but what I try center crop is just center crop the bounding box, the resize image from the bounding box. Yeah, I also try to just like crop off the other area not in the bounding box, but that will actually decrease the performance.
Okay, I see. Thank you.
So when you cropped everything else outside of the bounding box, then it got worse again.
Yeah, it got worse. Like I just try to like, so I just generate binary matrix that the matrix is one. If the pixel is one, it means the pixel is the bounding box. Otherwise, it will be 0. I just multiply this matrix to images. That means all of the others become 0, but it will just the performance just significantly decrease.
Was the binary matrix different for every image?
The binary matrix just I think it's just a mask.
For all images?
Sorry?
For all images at the same time, or is it different from image to image?
It's different. It just it just generates along with the bounding box the object information.
I mean, I can believe that that it drops. Basically, if the neuron looks at that part of the image, you're introducing another signal which might confuse the model. So if a neuron is actually looking there, I can totally believe that this decreases performance, because you pretend there's something in the image which is actually not there.
Yeah. Okay, thank you. Any more questions? Okay, if not, then let's thank Kaiwen again, and also congratulations for your first prize in the Sensorium track. Very nice. And yes, let's go to Sensorium Plus. We again have 3. So now we have 2 talks. So Kaiwen won both Sensorium and Sensorium Plus, and Sensorium Plus he was 2nd place. And then let's go ahead for the Sensorium Plus 3rd place. So Kirill, the stage is yours.
Hello, everybody. My name is Kirill. I'm from Technology Innovation Institute in Abu Dhabi. We make 3rd place in Sensorium Plus. But okay, a little background. We never work with neuron data or something like that. We mostly work with probabilistic models. So it was interesting deep for us. We also joined pretty late in like September, but we tried several kind of simple approach. The first one was augmentation, but as Kaiwen mentioned, the affine transformation obviously wouldn't work just because it would mess with positions. But we also tried something that wouldn't do affine transformation, like contrast, color jitter, salt and pepper, etc., but it wouldn't improve significantly, and especially on the validation. Another approach that we actually tried to replace readout with transformers. There is a thing that's called detection transformers, which is used one kind of interesting thing which called Hungarian loss. Basically, it would split the image on the boxes and try to make one-to-one association. So what it would say that one box is associated with one neuron and other neuron couldn't be associated with this part, but it wouldn't converge in our case, unfortunately. I believe maybe it would be more data because transformers famously know that they need good one, because we use it actually in other competition for the detection kind of for segmentation, but it would be like hundreds of thousands samples. So maybe that's the reason. another thing that we tried that actually worked somehow, it was kind of calibration, but we noticed that the distribution between prediction of the model and the neurons itself, if you kind of build the histogram, is not, is a kind of different. So we just make a simple transformation on applying the power of that exact power we would find on the validation, small validation set. And it actually would improve results a little bit. But okay, the thing that actually help us is just ensembling. So our method was kind of baseline of how far you can go just by subject models, and we just used like about 20 models because we noticed after that it wouldn't improve on the validation. And yeah, so that was it.
Okay, thanks a lot. Are there questions for?
Thank you.
Yeah, ensembling. Yeah, ensembling seems to be the way to go. Thanks, thanks a lot, Kirill.
Okay.
I actually have a question regarding data augmentation, because in principle, you could just transform the readouts by the same transformation. Did anyone try that?
Yeah,
Multiple people seem to have tried augmentations.
Yeah, I was feeling, but I started to try to implement. It was like at some point it was kind of too convoluted for me, so I like tried other things.
Okay, thanks.
Okay, any more questions? Yeah, then thanks again, Kirill, and congrats on your winning position. Yeah, then let's go to rank 1 of Sensorium Plus. Adrian, please go ahead.
Okay, so hello everyone, my name is Adrian Hoffmann, and I'm a neuroscience PhD student in Friedrich Helmchen's laboratory at the University of Zurich in Switzerland. And in my main PhD project, I work on visual and tactile integration of object locations in the mouse cortex. And I create kind of the same data that was used in the Sensorium challenge, just like different modality. So I'm showing a moving pole to the head fixed mouse, which creates tactile and visual input. And then I record data with 2-photon imaging in the mouse cortex to then understand what's going on. And I also started to use encoding models to then discriminate what is visual and that is what is tactile tuning. So therefore, I was very happy to hear about the Sensorium Plus challenge, and I wanted to participate. So the baseline model can be summarized like this, where the image and some behavior is the input, is fed through a model, and then predicts the activity of a single neuron. But as we know, cortical neurons are embedded in brain internal circuits, as well as receiving external information. So for example, they are embedded in dense circuits of interneurons locally within their circuits. Then they take part in larger cortical networks, and they're also embedded in a lot of loops with subcortical structures. And this internal brain activity has been shown to differ from the stimulus activity, for example, by Stringer and others. They looked at this and found that the activity they find as kind of behavior-driven activity was spanning a different subspace than the stimulus activity. And also in this data set, based on the design of the stimulus activity can be not correlated in time between samples, but the brain state can be correlated in time. So therefore, my idea was to look at temporal aspects of the data. So I sorted the given activity both by time and then also by neurons, by putting correlated neurons nearby with the raster map embedding. As you can see, there's a rich temporal structure in the data, hinting at a large contribution also of the brain state. And looking at the residuals of the provided baseline model, one can see that this model can only account partially for this activity, with red being overestimation and blue underestimations. So therefore, I decided to add a modulator network, which to account for these brain internal signals by adding the brain state, which knows the brain activity of previous time steps. And to go a little bit more in detail about this model, so the idea of extracting the brain state is the following. So the network state should be similar between time points, whereas the stimulus activity will be different between time points. So therefore, I extracted the network state by using a reduced rank autoregression, where I regress from the last time point to the next time point through a bottleneck, and then use the activity in this bottleneck through a non-negative matrix factorization to make it positive, and then as an input to a modulator network to give it more information about this brain state. Some other improvements I did was to normalize the behavior, to scale it between 0 and 1 for better matching between sessions. Then added the history per neuron by using a filter bank, and then also adding an output gain, which is shared across neurons and is smooth in time. And these percentage values are comparisons from the baseline to the test data when only using one of these elements. Additional steps were to then also use an ensemble network with 5 models with different seeds and test validation splits, and then also some hyperparameter adjustments. But if tested on their own, they had like a negative improvement. And the code is also now publicly available in my GitHub repository if you want to check it out and maybe incorporate some of these ideas. And finally, I would like to thank my supervisor, Friedrich Helmchen, for the freedom to pursue like this project, and Peter Ruprecht for helpful discussions and the computing infrastructure. And finally, also the Sensorium team, which really made this possible by providing a very good baseline model on which I could build this small thing. So thank you.
It's a very nice graphic. Thanks a lot.
Can I ask a question? Thanks, it was a great talk. So if I understood correctly, the dynamics, like the brain state, you're learning it from neural activity in addition to the pupil and the running? And then
Yes.
how do you use that, in the test set? Like what is the input? Because the test set is sort of randomly, there's no dynamics, there's no information about the neural dynamics in the test set, right? So maybe I missed something, I'm sure.
Yeah, so the training and test sets, they are interleaved because you don't want to show, I think, in the data set like too many test images in one block.
Mm-hmm.
And in the data set, like the timestamps for like all the trials were given, including like the test trials. So therefore, for every test trial,
I see.
one then knows the next.
I see. So you had the
closest.
time, you had the time step. Okay, I didn't realize. Okay, so you knew the time that the test data were coming from, so you knew the brain state based on that.
Yes, but then one can use the brain state from the nearest and training data point in the past. So this is still a causal model.
I see. And then did you try and break down the brain state because you also modified, if I understood correctly, your gain modulator also took the pupil into a different way than in the baseline model, right? You also modified that. Did you try and break down the contribution in your improvement in performance over the baseline between improving on the way you're using the pupil and the running versus the neural activity?
Yeah, so these are, so all the models I trained still contain the pupil and the running. So I didn't compare it to the stimulus only data set. So these are all like that they already have access to the pupil and the running.
And so you all,
Go ahead.
so you
Go
always
ahead.
had them as channels, right? So the input of the behavioral parameters to the model were as channels in the input with the image, right?
Yes, yeah, as that was in the baseline model. Yes.
Okay. Great.
Great.
And
Thanks.
and the modulator network, how did that work? So you basically just learned a gain on the predicted neural response from the readout, or how did you modulate the response?
So modulation is normally by then like adding these two terms, then applying with like learning like kind of the weights like per neuron, like how each neuron is influenced by its history, and then by this like network state which is 10-dimensional. So these are simple weights, and then I pass it through the nonlinearity, and then afterwards I apply like this gain term. But the order did not matter too much, so it could also have been like in another way.
So just that I get this right, so you have the original features from the convolutional network, and then you have these extra features. You just add them linearly in the function, and then final nonlinearity and some learned gain. Correct?
Yes. Yeah.
Okay. Thanks. Yeah.
Yeah. Thanks a lot. Any more questions? Okay, then thanks a lot. Yeah, and yeah, congrats again on winning the Sensorium Plus track. Yeah, very cool work. Yeah, so now this has been the talks of the winners. So we saw 5 or 6 approaches now, all very impressive. And let's now introduce Dean from University of Washington and giving a talk about the evaluation matrix and yeah, his views about it. Thanks a lot for agreeing to speak today, and welcome.
Thank you. I'll just share my screen here. So I should say I'm not at the University of Washington anymore. I'm at the Princeton Neuroscience Institute now, but my heart is definitely still in Seattle. So
Okay. Yeah.
Not a mistake according to my heart. Okay, let me see if I can hide this. Okay, so I've got a little bit of time. Okay, so I'm Dean Pospisil. I'm a postdoc in the lab of Jonathan Pillow at the Princeton Neuroscience Institute. And I was honored to be asked to speak here today. I'm over to get to do some preliminary analyses of the Sensorium competition models. I'm very excited to share some of these results, but also discuss important issues to consider when evaluating scientific models. And probably the most basic idea that I'm going to try to get across today is that evaluating models' raw performance on a held out set of test data often means that your estimate of performance now depends on the amount of data that you trained your model on and how data efficient your model is, which can sometimes be irrelevant to many scientific questions and obscure promising models. So I think it's just something to think about. At this point, you may be wondering about the picture of a rocket ship. This is meant to be a motivating analogy for an alternative estimator of model performance that I will present today. So that in that analogy, the data is the rocket fuel, your model is the rocket, and the moon is the accuracy that you desire. And one way of getting to the moon is to collect a bunch of rocket fuel, put it in a bunch of different rockets, and see how far you get. This is your classic data competition. And typically you don't make it to the moon, and it's unclear why. Perhaps with more fuel, you could have made it. Another way of getting to the moon is to measure the characteristics of the rocket ship, then use the laws of physics to figure out how much fuel you will need for the rocket ship to get to the moon. This is what NASA did, and it worked really well. Today, I will present an estimator that determines if all your model needed was more data to get to the moon. So let's go to the talk outline. First, I feel like this might be redundant for a lot of you, but I'll just give a sense of what the tuning curve is, because at least in the Sensorium track, that was what everyone was asked to predict, and just give some history of why we find the average response interesting, average neural response. Then I'll just talk statistically what leads to prediction errors in models that are made to fit to tuning curves. It should be no surprise that it's bias and variance, but there's two very particular sources of variance. One is not having enough repeats to average away neural variability when you evaluate your model, and the other is variability in estimates of your model parameters. I'll then run a simple simulation to show how these sources of variability affect methods of estimating model performance via R-squared, and demonstrate a method that only measures the bias of a model, not the variance. But this is, I should say, just to start out, because that sounds kind of incredible, this is for linear models in particular, but you can do a lot of stuff with linear models. Finally, I will get to the good stuff. I will show that an ensemble of all the models submitted to the Sensorium competition have very little bias and do far better than any individual model. And with enough data could achieve surprisingly good performance. Okay, so what's the tuning curve? The tuning curve is, at some point, a neurophysiologist, electrophysiologist stuck an electrode into the brain and was recording from a neuron and started showing stimuli to an organism. And this is what it looked like. So I'm going to be showing stimuli here. They could be anything, but here I'm going to be showing oriented gratings, and then I'm going to be recording the spike count of the neuron as those gratings are shown. Oh, that didn't. And at its essence, the sensory neuroscientist asks, what is the relationship between, at least the visual sensory neuroscientist, what is the relationship between this stimuli and the number of spikes and any other covariates that you're interested in? And so though the neurons are noisy, which is to say, from trial to trial, given the same stimulus, you get different responses, you eventually see a clear shape emerging. There is a typical degree of response. And so typically what an experimentalist will do is they will take these trials, these repeated trials, so that's in gray, and they'll average them. And to try to get a smoother curve to sort of see what's going on, absent the noise, they'll try to collect more trials, and they'll collect even more trials. And finally, if you collect infinite trials, it'll converge to something that is the theoretical tuning curve of a neuron, which is the expected spike count given the stimulus, some theoretical function that we don't have actually access to, but we can make inferences about it. So this idea right here, estimating and characterizing the tuning curve, is the most common research activity in sensory electrophysiology and has been a very productive area of research. Characterizing the tuning of visual neurons for an arbitrary image is a holy grail for visual neuroscientists and something that all of you have contributed to in the Sensorium competition. So thank you. And so now I'm going to move on to, well, what are the sources of prediction error when you have a model and you're trying to estimate how good it is at predicting the tuning curve and fitting the tuning curve as a function of some stimulus parameters, even if it's just pixels. So one source of prediction error is unexplainable variability because of finite repeats. Simply that even if I have a perfect model, so here I'm simulating from this expected response of a Poisson neuron, my sample averages will not perfectly align with that. There is noise from trial to trial. And so even if I have the perfect model, if I correlate that with the average spike count, I'll get an R-squared of 0.32, much lower than what it is theoretically, where I have actually chosen the perfect model of the tuning curve. If I increase the number of trials, R-squared will slowly go up and up. And eventually with enough repeats, you'll see, oh, I actually did have the perfect model. But it's typically impossible to collect hundreds of trials for most experiments, and more typically 3 to 10 repeats are collected. Thus, this is a common problem, accounting for variability in the estimate of model fits. This is a solvable problem. This is something that I worked on in my thesis. I created an estimator, one of many, a long line of estimators that have tried to correct for this problem. So here's the average R-squared for a simulation from this tuning curve, where the estimated R-squared is on the x-axis, and this is a histogram of the values. And R-squared tends to report that that the model is not a good fit. but with a correction that I made, r hat squared ER, it tends to consistently report that, yes, the fit is actually perfect, even though we only have a few repeats. And it's essentially you estimate the trial-to-trial variability, and using that, you can correct this r squared for the trial-to-trial variability. Also in this paper, we looked at many other estimators that have also attempted to make this estimate. Ours was only marginally better than all the others. Many others that were used. The one that was used in the competition was the Phoebe estimate. It pretty much does exactly the same as ours. But I'll just warn you that there are other estimators that are still in use in the literature, and you can check out our paper, that are actually very biased, sometimes upward, sometimes downward. And so just so you know, there are sets of estimators that have been validated, and there's other ones that have not, or don't work so well after being validated. Are there any questions at this point? Okay, great. Continuing on. So the other source of error in prediction is variability at least with respect to variance, is variability in parameter estimates because of finite observations. If I don't actually know what the coefficients of my true parameters of my model are, I just know the form, say the amplitude and the position of this tuning curve. Those are unknowns, and I have to fit them to data. From data sample to data sample, I will tend to misestimate that and thus not get optimal model performance. And so that's another issue. And finally, there's just bias, which is maybe the form of my model is wrong, and no matter how many repeats I have and no matter how many observations I get, my model is not going to improve. And I think this is probably, to me, the most scientifically interesting quantity. Because this says that my model is systematically wrong. Not that I didn't have enough data for my model, but whatever my assumptions, whatever went into that model, it doesn't fit. It can't fit this state of reality. But it's hard to estimate bias in complex models in general, especially for models that are non-convex in their optimization or are complex in their optimization, and we can't look at the distribution of those fits isn't in closed form. But for linear models, we can, and it's a very old technique. It's just that has been used for a long time to adjust for the degrees of freedom of a linear model to get an estimate of what the optimal fit would be. So now that I've given you sort of a soft introduction, we'll get into a little bit of what the assumptions of this model that I'm then going to perform analyses on the data is and run some simulations. So we're in the multivariate regression setting, linear regression, where this is a little bit different than what you see in that we have two sources of noise. First, we have some set of features, this XS, it's a vector of features that we're sampling from some distribution. This could be the features from your neural network or from your convolutional neural network, sampled from image to image. And then you have some linear transformation of those that is equal to some component of either your response in a particular neuron. In addition, there's some deviation from this true model that is systematic. And then finally, there is trial-to-trial noise. So these two are indexed by S because they are the same for each stimulus, whereas this one has an index N because it changes from trial to trial. It's independent across trial to trial. So you have these two sources of noise, systematic deviation and trial to trial noise. And we want to correct for this one and estimate what this is so that we can understand what is the optimal performance of this linear model. So our goal is to estimate this quantity, the expected value of y minus beta transpose xs. What is, given that we have the true parameter from which this model was sampled, what is the amount of residual variance? And then we can take that and we can normalize that to be r squared by normalizing by the total variance in y minus the variance that is just due to trial variability. And that's our goal estimator. And so in our simulations that I'm going to show you, where I try out different estimators to see how they get to this estimate, I'm going to call this true model performance. And we'll see how different estimators approach this quantity. So here's a a simulation that I'm going to run. On the y-axis is the estimated R-squared for different estimators that I'll try. And then I'm going to try it for different amounts of data. So whatever M samples that I have, and I have 250 features in my regression. So let's first try the naive correlation coefficient between a regression model and my data. So this is R-squared on training data. And so the first thing to notice is that if my number of samples is less than my number of features, then I get perfect performance every time. This is overfitting 101. And as my number of samples goes up, my performance goes down because I'm not able to overfit the data quite as much. And so this is why people do cross-validation, or I've held out test sets. So let's see how that does. So this is the R-squared on test data. So I fit the beta. I get an estimated beta hat, and I estimate this quantity, this R-squared on test data, or just I estimate R-squared on test data. And what you see is that the performance is very poor, and it slowly increases as the number of samples increase. And this is because I don't have the true beta when I'm estimating this R-squared. I have some noisy estimate of beta, and that reflects in the performance. So this is what people typically use in competition workshops, but it doesn't reflect the fact that with more data, the betas would have converged to the true beta, and you would do better. Now, for a long time in the literature, there has been the degrees of freedom correction for R-squared. It's called R-squared adjusted. It was invented in 1929. And basically what it does is it says, okay, for every feature that I add into my model, I have an expected amount of fitting improvement if I just expect it to be by chance. And so the nice thing about it is, even though it's still underestimating because there's still noise added to this, it's not accounting for the additional noise from trial to trial, it's flat with respect to the number of samples. Increasing the degrees of freedom of your model isn't spuriously improving fits when you go in this direction. So finally, what I did is I took this old method and I smashed it together with my newer method, and to give us an estimator that is an estimate of what's the performance of a model in the absence of noise, and if you had infinite data. And that's the basic idea. So let's apply this to data. So just for comparison, I will have the winning model, the performance of every neuron in the winning model using my noise corrected metric. So every point is a neuron, and then I'm plotting it as a function of its SNR, because there's certain interesting results that come out with SNR. So when I say SNR, it's just the signal to noise ratio. Just for an intuition, here's a high SNR neuron from the competition. You can see that the deviations with respect to stimulus are very large relative to their variance. Whereas for a low SNR neuron, it's not totally clear that there is an even is true variation in the tuning curve. And so the first thing that I noticed was the high SNR neurons tended to be fit much better than the low SNR neurons, which makes sense. There's sort of less signal to fit there, even though we're correcting for noise. Just because it's hard to look at this, I did a rolling average, including 500 samples at a time, so that you can see what the sort of average trend is here, and also because these estimates can be quite variable. Now consider this cow. How much does this cow weigh? Perhaps you have heard the story, and I kind of feel like this got revealed through all this ensembling, but the scientist Jonathan Galton collected the guesses of many people at a fair as to the weight of a cow, and to his surprise, he found that the average guess was more accurate than the individuals. And this has been termed the wisdom of crowds and is an intuitive motivation for ensemble models. And I wondered whether we might see a similar effect across the 120 submissions to this Sensorium competition. If we get to choose an optimal linear combination across the different submissions, how good can our performance be? So how I did this is I took all of the models for every neuron and I did PCA on them. So the first PC we would consider the sort of most optimal, the most common sort of form of prediction across all of the different models. And then I tested that on the held out test data using my noise and degree of freedom corrected estimator. And so the thinking being I would take the commonality amongst all models as my model, and I found it performed pretty terribly. Then, to my surprise, I tried two principal components, where for each neuron, I found the performance of the optimal linear combination of the first two principal components of all submitted models. And to my surprise, for higher SNR neurons, it outperformed the winning model. So here you can see it's outperforming the winning model, whereas it dips down for the lower SNR neurons. And so it did seem like the diversity across models is important. You're not just looking for the most common thing. And so I decided to keep going. And so this is 32 PCs across all models. And this gave me another bump in performance, and now it was outperforming in terms of this tail, these lower models. And you can kind of see where this is going. The highest I can go is up to, well, here's 64 PCs. We've got another jump. And finally, I went to 90 PCs, which is pretty much the highest we can go. And we're getting around 0.9 performance for these top neurons, and we're saturating down around 0.7. So we're doing far better than the winning model. Now, the huge caveat here is that this is a hypothetical model. This is assuming that you had infinite data to train on. And something I'm still working, and I still want to look into, is actually how much data would you need to achieve this model, because if you actually test this model on cross-validated data, its performance is down here, because these estimates of the betas on each of these different PCs is very highly variable. You're fitting 90 parameters to 100 data points.
Can I ask a question?
Yeah.
So, I mean, it's very cool, first of all, but my question is, it could be that, let's say, basically you learn, since you're cross-validating across images and not across neurons, you know, like some models are better at predicting some neurons and other models are other neurons, and you're weighing them like that, right? Is that?
Yep. Yeah. So if every model predicted one neuron better than every other model, then it would weight that model the most.
It will weigh that, because for each neuron you're learning a different way.
Yeah. Each neuron gets a different model, different
cool.
weights across the model.
Yeah. Okay, cool. Thanks.
And so one thing I should say is that, you know, this is all based on a statistical model. These are preliminary results, but, you know, I run simulations. The statistical model in simulation works fine, or it works as expected. But it's certainly, there needs to be more assumption checking to be done here to determine these results before, you know, you start making decisions on its basis. But it is very exciting because it is a fairly simple statistical model with fairly common assumptions. So in summary, the expected raw performance on test data is dependent on the amount of data and its interaction with model efficiency. So that's something always to keep in mind when comparing models in scientific context. I presented an estimator for linear models that are not dependent, which I think could be very useful when comparing models. You know, one place this could be used is on the outputs of neural networks. You could see what's the optimal performance of sort of a set of responses instead of just the final response. And I presented some evidence that with more data, ensemble models from the Sensorium competition could achieve near perfect performance. That's a little overstating it, but very good performance on well-tuned neurons. And then I leave it up to discussion of what we would do with such a high-performing model. It seems very exciting, but certainly goes back to questions that Konstantin brought up of sort of how do you use these then raw predictive models. And finally, acknowledgements. I want to acknowledge the Sensorium team for letting me look at this very cool data, get to analyze it. It was very interesting. Konstantin was a huge help in getting a lot of it organized, and Paul was very generous with his time in helping me get some of the data to do these analyses. I want to thank all the Sensorium competitors for submitting all this, doing all these interesting things and diverse things. And I think it's kind of cool that, you know, it seems like your diversity, sort of the fact that you use these lower principal components, was the thing that could lead to really great performance. And finally, my advisor, Jonathan Pillow, who said yes when I asked him if I could work on this. I greatly appreciate that. Questions?
Fantastic talk. Thanks a lot.
Yes,
No problem.
thanks a lot. I have a question about the cross-validation curve. So like you showed the validation performance for the model with 90 PCs. So that I would expect that to go up if you use less PCs. So basically that's just like very strong overfitting what we see here. That's true, right?
Yeah. Well, yeah, that's one way. Yeah. You can think of it as overfitting. You can also think of it as noisy estimates of your betas, but I think they're pretty much equivalent. Yeah.
I see. Okay.
I also want to follow up on this. Are you done, Fabi?
Yeah, go ahead. I think a little bit.
Yeah, thanks a lot, Dean. That really got me thinking. Now, one question I have, what happens if you take random models here and ensemble them? Because a lot of these models actually aren't good at all and aren't performing well. Would you get the same answer by just generating random predictions?
So the only thing that I checked just to make sure that this wasn't some kind of weird overfitting thing is I randomized the responses of the models relative to the responses of the neurons. And that, as expected, gave me 0 performance. But I don't know if that exactly gets at what you're asking, which is like—
No, that's kind of what I was wondering, whether you're just overfitting to a random basis or whether there's actually information
it does seem there has to be a relationship. Yeah.
Okay. All right, thanks.
No problem.
So like then I follow up. So your method for estimating the best performance, that holds for the training set or also for test held out data.
Yeah, it's an estimate of the predictive performance. So on new data, assuming that it's drawn from the same distribution as the data that you are fitting this linear model, then it's an accurate estimator of what the performance would be on held out data. Is that?
Yeah, then I just have I'm trying to wrap my head around that statement and the fact that the 90% model overfit so badly, or like what the estimate was so noisy. Because that is held out test data, right? So
what I did here is I said, okay, I'm gonna fit. So this isn't exactly equivalent. So I fit to 75% of the data with a linear model across these 90 PCs, and then I tested that on 25% of the data. So it's not using quite the same amount
Could it be that, because I agree with Fabian, it sounds, because we were discussing here. So you're showing us the test performance and you're saying the test performance is 0.9, right? In the assembly model. Could it be because the validation is single trials? And now you're having a noisy estimate of that. And somehow that's why you are, because why would the validation data be so much worse than the test data?
So
you know what I mean? Like we're kind of comparing apples with oranges somehow because of the way you're doing the estimated R-square. Because the validation data, there's no repeats, right? They're single trials.
So I think there might be a semantics. So I'm splitting the data up. So I'm, for all of these simulations, I am using the 100 test responses from the Sensorium competition. Yeah. So it's always these same 100 responses.
Yeah.
And then I'm doing cross validation to estimate what the performance of this would be on a held out set of data. So I'm fitting a linear model across these 90 PCs, and then I'm testing on a held out set what its actual performance is here.
From this 100, we call this like from this 100 oracle data, or from you split the train. Let's say you have 5,000 images for training, and you're using some for feeding the linear model to learn the combination, and you have a held out set for testing. But these
So
are individual trials.
So I'm only using 100 images, or like officially these are responses of the models to 100 images.
I see.
So there's no 5,000 images here.
Okay, and what about the final test set?
It's a limitation.
This is all on the final test set.
It's basically what we could provide to Dean as from the infrastructure of the competition. So what all the participants uploaded were the predictions only on this 100 test images and their repeats. So the predictions of the training data is not available for all the models. So yeah, then what Dean has access to here are the 100 images of this, or either the final test or the live test.
I see. Yeah. I see. So the final test is the final test basically of after the competition. This is the final test of the stuff that, because there was two, like there was the online test and the final test. The cross-validation is for the online test and the final test is for the final test. I still, maybe we can talk about it later. I just don't understand this huge discrepancy between the CV90 and the 90 PCs.
It's between the dashed and the solid here. That
I just don't. There must be something I'm missing, fundamental.
Okay.
So, do I understand it correctly? The solid line is an unbiased estimator of if I had infinite data, and I were to estimate the weights for these 90 principal components, correct?
Yes.
Now, didn't you show before that that estimator is unbiased only if you have more data and samples in one of your previous slides? Because with 90 principal components, you're close to 100 images. So you're probably in the range where your estimator is overestimating if you go back a few slides. So I'm inclined to think that you're just here. So basically you're in the regime where your red thingy is at 1.0.
Well, so I'm not there yet. It's still an unbiased.
But you're very close. I mean,
I'm close, but I'm not there. And it's still, the statistics still work out.
So where's the red line at 250? Because here you have 250 features. Is it at 0.5 or is it at 1? Because you're very close with 90 features, right?
Yeah, I am very close with 90 features. It's true, but I mean, it's the expected value is still the same. I mean, statistically, once I get to 100, yes, then there's a problem, and this estimator doesn't work. But until I get there, I just get a noisier and noisier estimate.
But this is under the assumption of a linear model, your previous thing. So could it be that with the nonlinear model, things fall apart earlier, and you just need more data to reliably estimate it?
A linear, I mean, I am testing a linear model, which is a linear combination of the submission predictions. The thing that probably is the hardest assumption that I make is that the noise is normally distributed. So I feel like I'm eating into time of the next speaker, so I can also take these questions offline. But basically, I do a variance stabilizing transform to try to get this to look more normal. It doesn't work as well if I just use the raw responses.
Okay, cool. Thanks a lot. Yeah.
Okay.
Let's take this offline. Thanks.
Okay, thanks a lot. Are there any more questions at this time? Then if not, let's thank the speaker again. Yeah, thanks a lot, Dean. And our second keynote talk of today is by Dr. Grace Lindsay from NYU, and she's working on using ANNs to build models about the brain. And let's welcome Lindsay, and please take it away.
Okay, 1 second. Okay, all good, I assume. Great. Okay, so I'm going to talk about some work that I did as a postdoc at UCL on building models of mouse visual processing using different forms of training. So the outline of the talk, I'm first going to give some background on the use of convolutional neural networks as a model of visual processing, specifically in the realm of training a model on a task and comparing it to the biology. And then I'm going to talk specifically about this past work that was done by a group at DeepMind on building a virtual rodent that learned through reinforcement learning, and then kind of dissecting the representations that these different networks that are trained with reinforcement learning and other forms of learning, what they learn about the visual input and how they compare and how they correspond to representations in mouse visual cortical regions. And then I want to just get into a broader discussion of what makes for a productive model under this kind of scheme of using these models this way. So as background, convolutional neural networks have been studied by visual neuroscientists for a while now, and in different forms. They've been around for decades. But one of the reasons for this this relationship between convolutional neural networks and visual neuroscience is the fact that the history of these networks is based in visual neuroscience work from Hubel and Wiesel, specifically the discovery of simple and complex cells. Simple cells respond to individual features at very specific spatial locations. So usually, a line oriented a certain way at a certain spatial location. And then complex cells also have a preferred visual feature, so preferred orientation in this case, but they have more spatial invariance. So they'll respond to the stimulus in multiple different spatial locations, and they get that response pattern by getting input from simple cells. So this was the basic model that Hubel and Wiesel laid out, and then through a kind of long history of computer vision and engineering, we ended up with convolution and pooling layers in artificial neural networks, with the convolution layers applying a filter that identifies a specific pattern in a specific location, and then pooling layers getting input from multiple of those convolutional layer units to give some spatial invariance to the model. And so you would kind of just repeat these processes over and over, and you get something that looks a bit like the ventral visual stream in biological vision. And so starting around 2014, these models were shown to, when they're trained correctly, they're shown to be able to produce representations and responses that are well aligned, at least in the space of existing models, well aligned to biological responses. So if you show an image to an artificial neural network and to a real neural network, through a human or an animal, and you record neural activity from the human or animal's brain, and then you try to predict that neural activity using the responses of convolutional neural networks, that was kind of surprisingly successful, again, based on the other models that we had to compare to at the time. And other forms of representational similarity analysis kind of show the same trend, that these models could be related to real neural activity, even though they're not trained on the neural activity. These are models trained on a visual task like ImageNet object classification. But so, yeah, these were models that were normally trained on supervised learning. And if we're thinking that this model is meant to be, a model of biological vision, supervised learning is not realistic because it requires way too many labeled images, and it usually requires backpropagation, which has its own problems in terms of being biologically realistic. So people weren't satisfied with the fact that you needed to do large-scale supervised learning on these models to make them good models of biological vision, because that aspect of it was not a good model of the biology. So then people started looking at unsupervised methods for training. And recently, specifically with the advent of contrastive models of unsupervised learning, the ability to train models without labels that still give you really good representations that can then go on to be useful for supervised tasks, those advances have helped in the modeling of the biology as well, because they at least don't require extensive labels. Which are not what you want if you're modeling the biology. So this was work from Dan Yeaman's group that showed that you can use contrastive learning approaches, which are the approaches in red in these models, and you can get matches to real neural activity in different brain areas that is on par with what you get from a supervised model. So this was showing that you can actually use unsupervised methods to create neural representations that are pretty similar to what you could get from using a supervised method, which is, a step in the right direction. But that leaves one type of learning left, and we're thinking about the kind of three main categories of learning, and that would be reinforcement learning. So what I'm going to talk about is mainly bringing in a model that's trained through reinforcement learning to ask how does the representation that model learns compare to models that are trained through unsupervised learning and supervised learning, what are those representations. And specifically, I'm interested I'm excited about the use of embodied reinforcement learning agents, because again, if we're really trying to make a biological model, the visual system doesn't exist in isolation in a rodent. It exists in a larger system that's trying to take actions that lead to good outcomes. And so to be able to have a model like that to think about vision in the context of, I think is really helpful. So one of the interesting things that makes reinforcement learning more significantly different from supervised and unsupervised learning than they are from each other, I think, is the fact that you do have an agent that exists in a world, usually a simulated world, but still in some sort of world, where their actions determine their own inputs. You don't have just a fixed data set that you train a network on, where the statistics of the input images are just set by what that data set is. Rather, the agent itself is determining the statistics of its input, and that can have interesting effects. I mean, in a failure mode, the animal just learns to walk into a corner over and over and never learns anything about the visual world or something like that. But just the fact that you have that loop in there is a little bit interesting, and the fact that the visual representations need to guide actions that then also guide the visual representations is just an interesting feature of reinforcement learning that really does make it different than the other types of learning. So the specific reinforcement learning agent that I worked with in the study is it's a virtual rodent. It comes from this paper that was put out by people at DeepMind, and this virtual rodent is based on the anatomy of a rat body. And you can see kind of the skeletal shape here. And then it has actuators, which are joint angles and tendons. So the output of this model is a set of joint angles and tendon positions that determine how this body moves in a physically simulated world. And then it has a sensory system that it uses to guide those movements. So it has visual input from, so the depiction of it here makes it look like it has two eyes and weirdly two teeth, I guess. But it has really a single eye in the center of its head. It has one egocentric camera that it gets input from. And then it has a few different proprioceptive sensors on its body to know when it's making contact with the world and to be able to know the position that the body is in. So that's the broad shape of the model. This is what's actually happening under the hood in this model. So it has a ResNet system that is the vision encoder that gets this egocentric camera input. It has just an MLP that serves as the encoder for the proprioceptive input that it's getting from its body. And then those go into some recurrent neural networks, which ultimately produce a distribution of action values that guide the animal's behavior. And as I said, those actions are in the form of joint angles and tendons of the body. So it's really low-level body control. It's not move forward and take a turn or anything like that. It's where are the animal's arms and legs placed in the environment and its whole body position. So the visual system here has to serve the purposes of those later goals. The tasks that the rodent is trained on are 4 different tasks. It's not explicitly given any indication of what the task is. It simply has to recognize the environment it's in and determine what the right actions are to get reward in that environment. So the first task is a gaps run task where the animal is running and needs to jump over these big gaps in the ground. And then there's a maze task where it has to collect a bunch of blue orbs in a maze, and a bowl escape task where it's placed in a valley with a kind of uneven terrain and it needs to be able to climb out of the valley. And then it has a 2-tap task where it needs to tap an orb and then wait a certain amount of time and tap it again. And that one is particularly based on some lab studies that rodents do. So these are the tasks that the animal needs to learn. It can learn them pretty well. This is an example of the maze test. What you're seeing on the left is that egocentric input. So that's what the animal is actually getting to make these decisions about how to run. But you can see it learns to move its body in a pretty efficient way, even though it has to learn from basic low-level controls, and it can also achieve the kind of higher task of actually getting the orbs. And here's the jumping task. So it's clearly using its vision to see that an upcoming gap is coming and do what it needs to with its body to be able to jump over that.
One question, in the jumping task, there's no reward.
It gets reward. Sorry, I didn't explain the rewards for each of the tasks. In the jumping task, it's rewarded for keeping a constant velocity. So however close it is to that target velocity. So it needs to be able to jump well to maintain that target velocity. In the maze, obviously for the orbs, in the valley escape, it's how far it is from its starting point in the valley. And then the 2-tap is how accurately is it tapping on this set schedule of one and then another tap. So yeah, so there is reward built into the running task based on the animal's velocity. Okay, so yeah, so this system as a whole is achieving that behavior, and the thing that I'm going to focus on now for the rest of the talk is this visual encoder, and looking into how it's representing this egocentric visual information that the rodent is getting. So this is the structure of that visual encoder. It's a small ResNet. So to be able to do this comparison, I want to hold the structure of the network constant across the different models that I'm going to train. And I'm also holding the data constant. So in this case, what that means is sampling images from the fully trained rodent as it explores its environment, and using those as the data set to train the other models that I'm going to describe here. So this is the architecture of all of the networks that I'm going to be comparing, and the data is all coming from the egocentric exploration of the virtual rodent. So yeah, so I'm gonna compare the reinforcement learning trained agents to 4 networks that were trained with supervised learning and 3 networks that were trained with unsupervised learning, and then also some random networks that aren't trained at all, just to see the impact of just random weight initialization. So the first supervised network is trained to predict reward. So this is given a single frame of input, the egocentric camera input, can you predict the reward that the rodent would get on the next time point in the task? And so there are times where this is going to be easy and times when it's going to be harder. You know, if it's kind of right on the verge of touching one of those blue orbs or something like that, you can probably predict reward fairly well. As you can see here, the model does capture some of this relationship between visual input and reward. The next supervised network was trained to predict the 3D rotation of the rodent in space. So kind of if it's tilted, if it's straight on, that kind of thing. So there's 3 dimensions there. These are the 3 dimensions. This is, you know, an intuitively much easier task to do with just the visual input, and the model performs fairly well on it. The next one is to categorize which of those 4 different tasks that the animal has to do, which one it's in, given a single frame. And so that for certain frames, that's going to be easier or more difficult, but on the whole, the network that's trained to do that performs quite well. And then the third supervised network is trained to do all 3 of those tasks simultaneously. And this is showing here in black the performance of this multitask trained network, which interestingly actually performs better than some of the single task trained networks. You get kind of a boost from having multiple objective functions in the same network. But so those are the 4 supervised networks trained to predict these kind of basic features of what the animal is doing at any given time. And then there are a few unsupervised networks. So the first is just a plain autoencoder that is meant to reproduce the images that are input into the model. So these are examples of the input images and the reconstructed versions from the autoencoder. And then a variational autoencoder, which has better performance in terms of actually reconstructing the images. So here are some examples here. You can see it's kind of capturing a little bit more of the visual detail than the plain autoencoder. And then the final unsupervised network is a contrastive predictive coding network, where essentially the the aim of the network is to be able to tell if two frames that it's being given are consecutive or not. So if two images came one right after another in the sequence of the animal doing the tasks that it was doing. And this contrastive predictive coding works fairly well, and it can end up doing that correctly. So this is just a summary of all of these different models. We have the 4 supervised models, 3 trained on individual tasks and 1 trained on all the tasks, the supervised tasks together, 3 unsupervised models, autoencoder, variational autoencoder, and contrastive predictive coding, and then also a random untrained network with random weights, and then the model that was trained with reinforcement learning, which is just pulled out of the larger virtual rodent architecture. And so they have different dimensionality to their outputs, and also, so in each case, I trained 3 different versions of the network just to be able to see the effect of different random seeds, with the exception of the actual reinforcement learning rodent, because that's too computationally expensive to retrain that one. So we have 1 of those and 3 of all the others. So then the question is, what's happening with these learned representations? If we look at the response of the neurons to these, to the images in the data set, how do they vary across networks that have the same architecture but were trained in these different ways? And I'm specifically looking at 4 different layers in the network. So the rectified linear layer that comes at the start of each of these large ResNet blocks, and then also the final output layer. And this final output layer, this 128 unit fully connected layer, is the only way in which the visual system goes on to impact the rest of the network. That's the only output to the rest of the agent. So these are dissimilarity matrices for the for 2 example networks, the reinforcement learning rodent network, and then a supervised network trained to predict the task that the animal was doing. So these matrices show how dissimilar the representation is for 2 different images. And these images are grouped according to what task the animal was engaged in. So you can see in the final layer of the network that was explicitly trained to classify the tasks that the animal is doing, you get these big blocks of low dissimilarities. So all the images from the same task look the same when you look at the response of this last layer of the network. And so that makes sense. That's how it's able to say these are all of the same task and be able to categorize tasks. You can actually see that block structure a bit in the reinforcement learning agent as well. But that obviously just emerges from what it needs to do rather than from any explicit training on the task that it's seeing. So these are the dissimilarity matrices. They're the basis on which I'm going to show results from representational similarity analysis, which just asks how similar are these dissimilarity matrices for different models. And as you can see, they're broken down by these 4 different layers in the network that I was talking about. And so this is the kind of general result across all the networks. So there are 2 kind of broad effects that you can see here. One is that you just have these diagonals that have these 3 by 3 squares of high similarity. Those are just the 3 different random initializations of the networks that were trained the same way. So that's reassuring that if you train the network the same way, you end up with networks that are pretty similar to each other. The random seeds aren't making that much of a difference. And then you have another broad trend across the layers, which is that in the first layer, things start out pretty similar to each other, according to this metric at least. Even the random networks that weren't trained at all are creating a response that's not that dissimilar from the response of the trained networks. But as you get to the last layer, things start to get far more dissimilar. So the actual output layers of these networks are starting to be much more broadly impacted by the different training regimes. And then within that, it's a little bit hard to see kind of the fine-grained comparisons across things. So this is just the average similarity that each type of network has with all the other similarities for each layer. So again, we see this broad trend of by the time you get to the last layer, the average similarity is way lower than in the first layer. But then you can also see that the reinforcement learning agent on average is a bit less similar than all the other ones. Its values are kind of lower overall, and especially at the first layer. So it is a bit of an outlier when looking at networks that were trained different ways. And I wanted to dig into why that might be in these networks. And so I'm going back to this image of the dissimilarity matrices, because there's a finding here that you might notice, which is just, so these plots are all in the same color bar. So the reinforcement learning trained network just has higher dissimilarity values overall. It's, you know, more yellow green here than this example supervised trained network. And that's true in general. It has higher dissimilarity values. So what that means is that any given pair of images, when you put it into the model trained with reinforcement learning, it's creating representations that are really divergent. It's not saying that any images are really like any other images. It's mostly saying everything's different from everything else. You're getting kind of a completely different response from the network for different images, which is not necessarily the case with all the other networks that are kind of using less of their representational space. And so digging more into that, I used a metric that's not uncommon in neuroscience analysis, which is the sparsity of the response. And so this is what's known as lifetime sparsity. It's a value that is 1 if the cell responds to only one stimulus. So if you have a cell that or a neuron that responds to one input image and has no response to anything else, then it has a lifetime sparsity of 1. And it's the value of this is 0 if it responds to everything equally. So it's a little bit like a metric of selectivity, saying that this neuron will only really respond to a few images, whereas if it responds to everything, that's not very informative. So that gives you a sparsity value of 0. And so this is a plot of all the networks for all the layers. And so you can see just within each layer and each network, there's a lot of different sparsity values for most of these these models. That's why kind of you have these long bars on the violin plot. There is a huge range of sparsity values, but there are some trends that you can see specifically with respect to the reinforcement learning trained model, where which is the last one here, where it does tend to be on the sparser end, so a higher values, so more cells that respond to only very few images. And certainly by the last layer, it's much sparser than all the other networks. So it really has a lot of cells that are very selective for specific images and aren't responding to images broadly. Another kind of related metric is the dimensionality of the representation. So as I was saying, if you have a network where the dissimilarity values are low, meaning that you put in an image and you get a response from the neural population that's pretty similar to what you get if you had put in a different image, that means that those networks aren't necessarily using their full space of possible responses. They're kind of using a limited range of how they could represent the image in neural space. And so dimensionality is also a measure of that. And so this is just looking at the number, the specific dimensionality metric I'm going to plot here is just looking at the number of principal components that are needed to explain 85% of the variability or the variance in the population response. So this is a somewhat common metric for roughly getting at dimensionality of the neural response. And looking at that across the different networks and the different layers, you can again see how the reinforcement learning trained network is a bit of an outlier, especially at certain layers. So so all of the networks have the same kind of baseline dimensionality because they have the same number of neurons. So that puts a cap on the dimensionality. But then the question is, how much of that space are they really using? And in the first layer, there's not too much variability. Some of the supervised networks are maybe having higher dimensionality, but at the second layer, the reinforcement learning trained engine is a clear outlier. It has a way higher dimensionality. It's using way more of its activity space than the other models. And the same is true for the third layer. And then also for the fourth layer, just one of the untrained models, the random models, happens to have high dimensionality. But for the most part, this reinforcement learning trained agent is showing much higher dimensionality in the neural response than the other ways of training these networks. And so I'm not going to get into it now, but I did do a little bit of digging to try to understand why this might be. Does it have to do with the fact that this, has to contribute to control of a somewhat high dimensional agent? I said, the body of this rodent has 38 degrees of freedom. But at the same time, the unsupervised autoencoders have to produce a whole 64 by 64 image. So they actually have higher degrees of freedom that they need to be able to control. So it doesn't seem like that's the reason. And exploring it, it doesn't actually seem like the visual system of the rodent is directly controlling the body in the immediate time frame. So the analyses that I did suggest that the visual system is providing input that lead to longer term goals in the rodent, and not through the direct control of the body. The proprioceptive input is more responsible for deciding what the actual next output will be at the next time step. So that's important to think about. When you want to understand a visual system that exists in a larger system, it could be being used for immediate response to the immediate task, but it could also be collecting information for longer term goals. Okay, but the comparison to real neural activity, how do these different models train in different ways? How do they do they at all capture mouse neural activity in different cortical areas? So for this, I'm using the Allen Brain Observatory data set, which has calcium imaging from a variety of cortical visual regions in the mouse brain in response to natural stimuli. And this is the result of doing this representational similarity analysis, comparing the models to the mouse data. And so what I'm showing on the X axis here is the different layers of the model, and then on the Y is the different brain regions, and then within each of these plots are the different models trained in different ways. So you can see there is some variability amongst the models. Some of them are producing much better fits than others. If you just want to know what can you do to get your best fit out of these models, it is the reinforcement learning trained agent, but interestingly, it's the second layer that I recorded from in this model that across the board is doing the best at explaining the different visual regions. And as you recall, this was the layer that had the most extreme results in terms of the dimensionality, being much more high dimensional than the other layers. And there's reasons to believe that that could be related to this finding. Yeah, so the second layer in the reinforcement learning trained rodent does the best in terms of correspondence to real mouse data across all of the mouse cortical regions. Now that is interesting. It's interesting the reinforcement learning agent is doing the best at this. What you'd kind of want to see from a modeling perspective is that there's a hierarchical relationship where the earlier layers in the model best explain the early layers in the visual system, or the early regions in the visual system, and later areas in the model better explain the more secondary visual regions in the mouse. And so that kind of, it's not what we find. It is what is found in different models, especially those aiming to model primate visual cortex. You can find a much better hierarchical correspondence there. And there could be reasons that relate to the mouse visual system that explain that the mouse visual system is less of a clean hierarchy than the primate one. But that just kind of leads me into a general discussion about what we want out of these models and what to consider if you want to create a modeling framework that's productive in terms of understanding biological vision. And so one is to call your model a mechanistic model, to say that it's kind of capturing the processes that are happening in the brain. The parts of the model inside the model need to relate to parts in the brain. So this comes up a lot when you have computer vision models that are really good at doing the visual task, and maybe they're even better than humans at doing the visual task. But then if you try to relate the internal parts of the model to the internal parts of the brain, sometimes you actually don't get a good correspondence there. And if you don't get that correspondence, then it's not really a mechanistic model of what's happening. You need to have internal parts that align where you can say A leads to B leads to C, and that's how we produce the behavior. And if you don't have a way to relate the parts of the model to the parts of the brain, then you can't really make that mechanistic claim. So the idea of using different learning mechanisms and even different task objectives and even different data, sometimes these are used because, as I said, The most basic form of supervised training on a large labeled data set isn't biologically realistic. And so people want to know that you can get good visual representations without having to do that. It's kind of a proof of concept. And that's definitely something that matters, is showing like, yes, there's a way to get a working visual system that doesn't require just using labeled images, because, you know, we know that that's not what the brain is doing. But also people use this to kind of speak to the purpose of different parts of the brain by saying, oh, I trained a model with this objective, and that model was able to, you know, fit neural activity in this brain area. So this brain area must be for this objective, that kind of thing. And I think I understand the motivation for that. And I think there's a little bit of, you know, something to that in terms of situating yourself into what role a brain area is playing or what role specific neurons are playing. But it definitely has to be done with caution. One, because as I showed, even untrained models, you know, if you show them an image and have them do some nonlinear computations on it, they might end up having a somewhat decent fit to some other, you know, systems that are doing something different. And also, when you have something like a visual system or any part of the brain that's in a larger system, in an embodied agent, the notion of this area is for this or this neuron is for this starts to make a little bit less sense because you don't know a priori that you can break down the larger goal and function of the system into neatly compartmentalizable things where you can say this part of the system does this exact thing, and I can model that, you know, without even reference to the larger goals of the system. I think that that's something that we do when we model the visual system and just train networks on simple visual tasks, and then kind of assume that, okay, then the visual information goes on to other parts of the brain, but we don't need to worry about that. But when you get more into it, when you really want to make a good model, you're going to have to start worrying about that. You're going to have to worry about how this information is used in the rest of the brain to understand it. Also, something that I didn't get into here because I kept the network architecture constant, but I have other work and there's other people's work that speak to this as well. It seems like neural network architecture, varying that, is not necessarily the best way to understand the role of structure in the brain. So neuroscience has a long history of caring about the relationship between structure and function, and the idea that you can kind of look at how neurons connect and say something about the computation that they're doing and the role that they're playing. In the world of machine learning, it seems like the details of how you train a network is influencing what it learns and how it works, more than the broad architectural features that people play with. And so if you want to say like, oh, I'm going to show that, you know, you need this form of architecture to do this brain computation, well, it's going to be really hard to actually prove that because you're going to need to vary every possible way of training a bunch of different architectures and show that it's a really robust finding that structural detail is necessary for some computation. And I think with the current setup of artificial neural networks and the way they're trained, it's not necessarily something that we can get a good grip on right now. And then finally, understanding, if you want to understand behavior, like the actual output of a system, knowing what aspects of the neural response matter is very difficult. And I think that this competition actually speaks directly to that because you have one track where you consider the trial by trial variability noise and you don't care about it. And you have another track where you're like, oh, wait, no, that's behavioral details, that's information. And so it really matters what you're trying to understand. You know, different aspects of the neural response, even if they're very reliable, they might not be relevant for a certain behavioral goal, and other, you know, details that might be smaller in terms of kind of effect size and their contribution to an individual neuron's response might be important for those things. So, you know, these things that we have for a long time called noise that seem to now be viewed as the result of movement and other things like that. Those things can be very important for understanding how an animal uses its visual system to move throughout the world. So that's really tricky, and that, I mean, ultimately kind of requires causal interventions and other things that are going to be difficult to get out of just fitting a model, I think. Yeah, so to summarize, the reinforcement learning trained network has different representational properties than the networks trained with supervised or unsupervised methods. And also this RL agent was actually able to provide the best match to the mouse neural data, but not in a way that matched any sort of hierarchy in the mouse visual system. And in general, when working with these models that are meant to to capture something about biological processing, choices about training, about architecture, and about how you evaluate and compare the model to the brain are all complicated. They're context dependent. They depend on your goals and how you're intending to kind of think about the model and its use. So I want to thank the collaborators from DeepMind, Josh Merrill, and my PIs at UCL, Tom Mershik-Flogel and Manish Sahani. Thank you.
Thank you.
Thanks a lot.
Can I ask a question, Grace? Thanks, that was a great talk. So if I understand correctly, you showed that in the reinforcement learning network, the dissimilarity between the images increased more as a function of layer than the other objectives, or you showed that for all of them, the lower layers where the images were more similar, right? And as you increase, as you go deeper, they become more dissimilar. But then you showed that in the reinforcement, here you showed that they're more dissimilar as you go higher up, right? They start being more similar among the networks in the early, like in R1, right? So you showed these two things.
So
right?
So these are results about how similar the models are to each other.
Yeah.
And so all the models are very similar to each other if you're comparing at the first layer.
Yeah.
But by the time you get to the last layer, the models become very dissimilar.
Also reflect the bottleneck effect, because you have low values to start with. You know, all the first layer, if you go to your previous slide, they're all low, those values. So you don't expect them to be, you know what I mean? Like they're just gonna be more similar because they're lower values potentially. Like they all, basically it's this, you know what I mean? Like in R1, the values are very low. So maybe that kind of put some bounds on being more similar to start with.
The metric that I'm using to say whether the models are similar or not is the Spearman rank correlation. So I don't think that should be impacted by the absolute value of the matrix values here.
Maybe a related, a more conceptual question is, so is it possible that if you, for example, you let's say with a variational autoencoder, right, use very simple scenes that they didn't have a lot of complexity, right? So if you, let's say, the same task, but now, you had these rewards, but the scene was much more complex. Could these things change and invert, like all of a sudden? Because, for example, even the fact that they are so similar in the first layer, I'm not sure if that's true, for example, if you look at VGG or some other network. You know what I mean? Like, I don't know if the similarity would be so low in the first layer because you have high spatial resolution in the first layer. Yeah, something like that's kind of my question. Like the complexity of the visual scene, basically.
Yeah. So it is difficult to do these comparisons using more natural images, just because you need to train the reinforcement learning agent in some sort of simulated world. And so how much are you going to spend on, rendering details of the visual environment and all of that? So yeah, we were limited in the visual data set that we could use to do these comparisons. To make it a fair comparison, all the networks had to use these style of images, which are simple for sure. When I do the comparison to the mouse neural data, I'm showing the networks, scaled down versions of these naturalistic stimuli. And I did do some of the same, analyses of the responses that the neural networks give in response to these stimuli, even though they were trained on the simpler ones. And I don't recall there being any kind of violations of the general trends that I found when they were showed the simpler images. But I'm not really remembering that in detail. But yeah, and also it's still talking about networks that were trained on simple images and just shown the more complex ones.
Great, thanks. Great, thank you.
Are there more questions for Grace?
I mean, maybe a comment. Maybe it's almost the same question that Andreas asked, but to me it seemed, maybe if I got that wrong, please correct me. But I thought maybe the reason why you see this kind of like a higher dimensionality for the reinforcement learning agent is that the output entropy that the network has to produce is somehow higher. If you have like a 4-class classification problem and you have to identify the task, that's an easier problem. And you basically need to produce 2 bits than if you have to run an entire 38 degree of freedom rat through a maze. Do you think that's related to that, to the complexity of the training goal?
Yeah, so that's something that we definitely thought about. So I'm showing here the output dimension for all of these networks on the right here. And as I said, the autoencoders actually have technically the larger dimensional output. They have to output an entire image. So you could argue that they should also have this kind of representation, but we don't see it as much in those. And then also I'm showing here the dimensionality of the actual action space. So not just the number of degrees of freedom, but the actual used kind of dimensionality, because there's correlations between those outputs. So yeah, you can maybe think that this is, approaching this action dimensionality, but also as I said, the visual encoder, it outputs this final layer, and then it goes through all these recurrent neural networks and things before it actually produces action. And so that fact, combined with some stuff that I didn't show here about trying to actually predict the action from the visual input alone, makes me think that that's not the direct reason. So basically, we tried to do imitation learning, where you just get a visual input frame. And the same way as I did the other supervised networks, the supervision in this case would be, what is the 38-dimensional output vector of the rodent? And the visual net, you can't learn that. You can't, with this network, you can't put in an image and learn to predict the action that the rodent took in response to that image. If you use the proprioceptive input, you can get a lot closer. But you can't do that with just the visual input, which was part of the reason why I think the visual input is driving more long-term plans in the network rather than the direct control of the body, which is admittedly more high-dimensional than a usual system here.
I see. Thanks a lot.
Maybe just one more related question, Grace. Have you thought though about trying, going back to Fabian's point, for example, if you look at your reconstructions, they're very smooth. So so the dimensionality, I mean, you do have high dimensionality, but the intrinsic dimensionality of those images is much lower, right? They live on a very low dimensional manifold. Have you tried to study the complexity of the latent space or other, on the VAE or something, like basically you try and add detailed reconstruction information to see if now you're starting to get higher dimensionality in the final layers or whatever, and then now you're feeding also the data better or something like that. You basically get a richer bank of features, because you're right, it's a high dimensional, but if I look at them, I'm like, well, these are really low dimensional.
Yeah, they have a lot of correlations. So in terms of pixel reconstruction, the regular autoencoder shown here does worse than the variational autoencoder. So I haven't explicitly tried to drive it even better, but we get kind of a natural comparison there. And then if I look at how that fits the neural data, so that's these two blue ones here, and the variational autoencoder actually doesn't do very well in fitting the neural data. So at least in this limited kind of natural experiment in that direction, that alone isn't enough to explain the fit to the mouse data.
All right, thank you. Thanks.
Okay, thanks a lot. Any more questions for Grace? Then let's thank our speaker again. Thanks a lot, Grace, for speaking at the workshop. That was fantastic. Then as our last point on the program, we'll discuss a bit about what we've learned. So this was our first year running this competition, our first shot at it, and I think some things went well, others we might improve. So I'll hand over to Paul for discussions and lessons learned. Paul, it's your turn.
Yeah,
No,
okay.
he's on it. Okay.
All right. You guys can hear me now? Perfect. So yeah, thanks everyone for coming. Thanks for all of our speakers. We just wanted to have a quick discussion here at the end of kind of some of the feedback that we've gotten, some of the discussions we've had about what kind of role a competition such as this can play, what kind of future directions would be most helpful to the community and to people interested in competitions like this. I think there are kind of 4 broad themes that I identified kind of in our thinking about how to move forward with this competition, and also in the feedback that we received. The first one was kind of this question about the overall goal of such a competition. It seems there's this kind of inherent tension between identifying high-performing models that have some constrained architecture in a way that provides some scientific interpretability, as we just heard about in the last talk, as compared to sort of high-performing black box models that don't offer that interpretability, but still help us to identify testable scientific predictions that we can go back to test in the real animal. And so initially, a lot of the use of these models in our lab kind of revolves around this second category. And so I was just wondering if anyone had any thoughts they wanted to offer in support of one or the other. I do think that there is also to consider the nature of the competition as a vehicle kind of limits what kind of approach is well suited here. For example, if you wanted to have the community joining in the scientific pursuit and closing the loop on those experiments may be more appropriate for like an observatory model rather than a community competition. So yeah, if there's anyone who had any thoughts on that.
I would say that I would always go for high performing Black's models first, just try to fit the curves. And then once you know that performance is possible as an upper ceiling, I think there's good examples of teacher learner networks where you can then distill that knowledge. Once you've sort of used a very large network or complex network, you now have this thing that can generate infinite data to train smaller models on. And so, I wouldn't shy away from black book models to start, because I think they'll be the first ones to get it, and then you can distill it down afterwards.
Yeah, I mean, also what we saw from the competition results, basically, maybe we were hoping for a model that was more maybe biologically plausible or like used something, and then the only thing I can remember was the V1 layer, which went into that direction, but everything else was basically very black box and very machine learning-y. And yeah, which is okay. I agree with Dean. I think I'd rather have a model that predicts well in the beginning, and then I try to make that match to some neuromechanistic implementation, than starting with something that might be too restricted or too hard to fit in the beginning.
Yeah, my thinking in kind of posing this question first was also that in the other areas for discussion, if there's any opportunities where it would be easy to integrate a more interpretable design to the competition, perhaps that's something we could consider. But yeah, on first blush, it seems like, especially with this type of vehicle, it's better suited to kind of pursuing these black box models and then pursuing the scientific interpretable models in a different structure, or at a later time. Is there anyone else who had any other thoughts they want to volunteer on this, or? Okay, so the next two items are a little bit more just logistically focused. Any feedback from any of our participants or any thoughts from anyone else in the call on, kind of the details on what was provided to the participants, any additional things that would make it a more accessible competition for people to kind of get their hands on, especially if they're not used to working with this type of data, or any positive feedback on things that people experience is going really well, so that we can remember to do it next year, or any negative feedback on things that we could improve on. That would be a good target for improvement.
I think one thing that could be interesting is to start looking at OOD generalization of these models. Like, for example, with corrupted images, or sort of try and test their robustness, because that may be a more stronger way to differentiate between them. For example, like, you add Gaussian noise or corruptions on these images, on the testing data only, because they are, it may be a better, also for the goal-driven models, like, if you learn better models, they should be able to generalize better outside the training set.
Yeah, not even that. I think even if you just try to have a test set with the with like classical neuroscience stimuli to produce tuning properties that you have measured before, I think that would be interesting.
Yeah, but I agree with Alex, without telling people. So maybe the next year competition would be less information about the test, because then I think, it opens it up also for this goal-driven stuff that Grace talked about. Just what is, because kind of where across the field, maybe overfitting, we know, but if you don't know, what, that would be a more interesting thing. I agree.
But from a technical perspective, makes it also more difficult, because then we have to retrain parts of the model. But yeah, otherwise I agree with Alex. It would be good to not know that domain, because otherwise you can infuse it.
Yeah.
As long as it's image computable, you don't need to retrain, right?
Yeah.
You can mess with images, you can mess with, I don't know, brain states would probably be a bit more tricky.
Oh, I thought, yeah, but then what do you mean by not providing the OOD? I think it's...
Well, we can, the question is how to implement it. We would need access to the model.
Yes,
but
exactly.
We could just show gradings. That would be very boring, but maybe something a bit more complicated. That's not quite standard, but...
Yeah.
Because if you provide the stimulus without the labels, then there's still a way of using third-party data and integrate that into the model somehow.
Yeah, exactly. So that's what I meant. We need to evaluate the model then, not just get responses. Yeah.
Yes, that might make it more challenging from just our infrastructure perspective. For sure, like I think it was quite easy to just have predictions in a CSV file that can be uploaded. But making the model accessible, might be a higher threshold, but worth it probably. Maybe in one track.
It could also be an evaluation post-hoc after the competition is closed. We release the test stimuli, and then people have to submit the predictions, but can't change the model anymore.
Yeah, something like that. So that it's more like the real world, the life. You get tested or stuff you're not supposed to know.
Even that would be a little bit practically tricky to arrange, though. I think, everyone get me your predictions in the next 24 hours or else, and promise you didn't change anything. So one additional question I had was how people felt about the timeline of the competition as a whole. It's kind of naturally constrained in this way where it'll likely start after it's been accepted by NeurIPS review, and we want it to end in time for the conference itself. which places a sort of upper bound on how long the duration could run. If we were to, for example, run this as a benchmark track instead of a competition track, perhaps we could divorce the timeline of the competition, and that opens up some options. So I was wondering how people felt about, whether this is something that'd be better suited by having more time, or.
Yeah, maybe some of the windows, if you, sorry, go ahead.
Yeah, I think the timeline was like reasonable. I think like 4 months is like enough time. And like also to the previous point of like the provided stuff. So I thought it was like very well kind of curated code and notebooks like to get started. I think especially like the data loaders and then like the baseline models, I think were like a really large help to then get started and then kind of be relatively quick, be at the point where one can try out some new things. And I think this was really well done.
Thanks a lot.
Did anyone else have any input on a shorter or a longer competition? Okay. The next kind of big category I had was kind of this topic of how to evaluate the models. Some of these questions that have arisen in our discussions are whether there might be some way to rank it on more than one dimension. For example, if you had many OOD categories, you may want to note that a model performed well in OOD in some categories, but not others. Another question is if there is some way that we may want to constrain the training compute, or in some way retrain the models ourselves, or get access to the models to test on some different category. I think all of these place a similar a similar infrastructure obstacle in actually running those models outside of the hands of the original creators. I don't think we're quite at the stage where we have to worry about large model infrastructure yet, but and then also whether we might choose to restructure the evaluation in some way that would encourage or discourage certain practices. For example, ensembling was a common strategy, but it's not exactly a new discovery as of this competition. So perhaps we would design in such a way to discourage that approach. And lastly, whether we might want to select some minimum improvement over baseline to select the winner. And that suggestion makes more context in the sense of a competition timeline that is somewhat divorced from the official competition track of NeurIPS. So I was wondering if anyone had any thoughts on any of those categories.
One thing I wondered about is why you assess performance on the correlation on a neuron by neuron basis, as opposed to saying, looking at the total variance of tuning across neurons. You end up weighting many sort of poorly tuned neurons into your metric, as opposed to sort of weighting more heavily those neurons which have strong tuning for visual stimuli. So that could be another way to assess how well someone's model is doing.
But that will also happen when you do variance explained, because you have to normalize the responses somehow, because the calcium signal doesn't have a natural scale. So you're going to amplify the noise of the low signal to noise ratio neurons when there's little signal.
So are you saying if you correct for trial to trial variability?
I mean, you will always have to normalize the responses of the neurons somehow, because the absolute scale isn't really meaningful in calcium data.
I guess the metric would be is you would get the covariance of the model with every single neuron, and you divide it by the total signal variance across all neurons. And in that ratio, the variance of the neurons that were poorly tuned would be small, and the variance of the neurons that were greatly tuned would be large.
Well, no, because you usually normalize the variance of every neuron to be 1, because the variance of a neuron is not a meaningful thing in calcium data. We're not recording spikes. We're recording something that's proportional to spikes, and we don't know the constant of proportionality.
Okay, well, it would be something that would be weighting neurons proportional to their signal to noise ratio relative to their trial-to-trial variability. What is their variation in their signal? I don't know exactly what that would be.
Yeah,
but there is certainly a strong correlation with the neurons with low SNR are the ones bringing the scores down.
Right. Good point.
Is there anyone who has any?
So I think in response to your question, Paul, I think it's difficult to tell people not to do ensembling or the like. I would rather make it easy to ensemble and have it be part of the baseline next time, and then everybody's doing ensembling out of the box and no one benefits from it. Because what exactly constitutes an ensemble, and how do you define that? How do you control that?
So one possibility I was considering is that we would, it's related to this final point, where we would basically ensemble our own baseline as much as we can, and then say you have to do better than the ensembled baseline in order for it to be like, you know, a minimum improvement. And that way people could still include ensembling in their approach, and we don't have to, you know, retrain models on our end to guarantee whether or not they're using ensembling, things like that. But at the same time, it would kind of, you know, select for submissions that, you know, we're celebrating something in addition to the ensembling. I do worry that it'll discourage people with fewer compute resources available, which is why reason, to my recollection, we avoided it in this year's competition. But
will the baseline next year be the best model this year?
But definitely won't be worse.
Yeah. Probably we will opt for a different data set. So for sure, this competition as it is will continue to run, and so hopefully just naturally it will improve. Yeah.
But I think there's something to be said about running the same structural competition again, be it on the same data set or not, but have a next iteration where in order to beat state of the art, you can't just pull the usual tricks. You actually have to make a design contribution.
so one option is that for the ongoing Sensorium benchmark, which will remain on the website, we could make our own updated baseline where we ensemble as much as we can, and we add that to the you know, registered entries.
Yeah.
Yeah, that's a good point.
Did anyone else have any other thoughts or feedback on evaluating the competition? In that case, the last question and kind of things to look forward to are how to iterate the competition for future years. So as the data guy, I'm super excited about the data side, but in discussions with kind of some of the other long-running competitions at NeurIPS, they emphasize that the thing they're looking for in innovation from year to year is some sort of change in, you know, the model design or architecture. So even if you had, you know, a data set that would be scientifically expanding important directions, like different areas or layers, if it doesn't really demand additional, you know, changes from the participants, perhaps it would not be viewed as a sufficiently novel addition to the competition track or benchmark track. But for changes in data, some things we've discussed are in the future adding more cortical layers, more cortical areas, moving into additional adjacent sensory areas, incorporating color stimuli, moving stimuli, moving from passive viewing into something that incorporates decision-making, animal behavior, and different recording techniques, for example, including electrophysiology instead of just optical physiology. And also some possible changes in architecture would be, moving from a static model to a dynamic model that is predicting something that changes per frame instead of the response to a static image, or incorporating a prediction of noise as well. And another additional direction would be kind of the task being to reconstruct the stimulus from the provided data rather than predicted data from the stimulus. So I was just wondering if anyone, that participated in the competition or any of the organizers see any of these as exceptionally interesting, want to put a vote in for something they'd really like to see in a future competition. Any other suggestions that they think would be an interesting thing to incorporate that would add something?
I mean, definitely. So go ahead, please.
So I think one additional variable that would be very interesting, especially for like the trial variability, would be like a video of the mouse, kind of like a face video, or like more high dimensional videos. I think there's also like now like a new paper from like Kausen Stringer's lab, like with like the space map like algorithm, where they achieve also like really high performances only on kind of using face motion to then describe visual activity, like V1 activity. So I think adding this to the competition, I think would boost like the explained variance like by I think really a lot, and maybe could put it like in the realm where it's then like very interesting to really have like high explained variances, maybe then also to look into what the model is doing.
Yeah, I agree with that.
This may be technically challenging, but being able to predict causal perturbations, such as optogenic stimulation or cooling, starts to allow you to constrain causal models and understand the relationship between regions or between neurons in a mechanistic way. So that could be an interesting data set to predict the effect of causal perturbation.
The list here that you provided, Paul, I think definitely the dynamic model or a model that predicts the entire response distribution, I think would be interesting from an architectural point of view. And that's actually something that like two types of models that need to happen and need to be pushed, in my opinion. I would not go for reconstruction because it's very difficult to measure reconstruction, because in the end what we care is how good can we perceptually reconstruct the images for this model system, and then how we're going to measure that except with another model of that system. If you measure it by pixel or with some other similarity measure, then probably we're just going to compete for who has the best natural image prior, and not who has the best reconstruction model. So I feel that this will be super hard to evaluate.
Yeah, it needs to be reconstructed for the mouse, not for the pixels, right? And there's no, we don't have the solid understanding of this yet.
Anyone else? Oh. With any feedback on things that they'd like to see in future competitions, things that they're excited for? All right, that was my last topic slide, so I'll hand it back off to Fabian.
To me?
Not Fabian.
Or to me. Yes, so that was basically it for our workshop. So there's one more thing. So last week we've been to NeurIPS in New Orleans, and there was this competition event. We had a poster there, and we were actually handing out for all the participants who showed up, and Simone showed up, and we actually made these cups for Sensorium, and we're gonna send those out to all winners, also to all speakers. So Dean and Grace, you also you'll get a mug for sure. And so with that, I would like to first thanks to all our speakers. So Dean and Grace, we're very happy that you've agreed to participate. Also Simone, Kaiwen, Kirill, and Adrian has been super nice that you gave this winning talk. Also thanks to participants who've submitted models. Yeah, we got a total of close to 200 models that were submitted. So that's, I think, really nice for our first try. And yeah, thanks to the whole team. This has been an effort of like 3 labs. So Andreas Tullias here in Baylor College in Houston, Alex Ecker in Göttingen, and also Fabian Sins in Tübingen and Göttingen. So yeah, thanks a lot to everybody for joining in today.
Yeah, particularly thanks to Consti and Paul for pushing it. Yeah, clapping in real.
Thanks a lot.
Thanks everyone.
Thanks everyone. Then have a good night in Germany, and yeah.
Enjoy the rest of the day in Houston. Bye bye. See you.
Thank you.
Thanks
Bye.
Bye everyone.
See you.